Hello and welcome. Let's have some fun. So today we will be solving Leetcode 78 subsets. So the problem definition is we are given an integer array called nums. It contains unique elements, and we want to return all possible subsets. Now the solution cannot contain duplicate subsets, and luckily we can return the solution in any order. So let's take a look at example 1. So the numbers you are given are 1, 2, and 3. And from comparing it with example 2, what you can see is that at every point we are going to have at least an empty array and an array containing the original array. But beyond that, we have all the numbers individually as subsets. So for example 1, that's 1, 2, and 3. And then there are combinations with different numbers as well. Now, this is a very good time to point out that subsets here are not equal to permutations. Why? Because for permutations, for 1, 2, you can also have 2, 1. But as we can see here, we can't return any duplicate subsets, so we are going to keep that in mind. So now this is a very good backtracking question, and the best way to go about implementing this is to think of it as decision trees. So to solve this, we are going to iterate through our array nums starting from the front, and at every time we are going to be faced with two decisions. Simple enough: to add or not to add. Now you're going to start with 1. So we can choose to add 1 to a new array we'll create, or we can choose not to add 1, so that makes it empty. And then we will move to the next number in our array, which is 2. And we are going to do essentially the same thing. So with our left choices, they are always going to be to add the current number. So this makes it 1, 2. And our right choices are always going to be not to add the current number. So that for this would mean that 1 is still going to be 1. And then we are going to do the same left and right choices for this subset here as well. So the left is going to be to add 2 or not to add 2, which will essentially make it empty. And now we are going to move on to our next number, which is 3. And our decision here would be to add 3, so making it 1, 2, 3, or not to add 3, which would just make it 1, 2. We're going to do the same for the next subset, which is 1. Here we are going to add 3, or not to add 3. And the same thing down here, to add 3, or not to add 3. Down here to add 3, or not to add 3. So if you can, I don't know if it's already become apparent to you, but these numbers here, these subsets here, correspond to the subsets that we should be returning. And you will see that so far we have traversed essentially 3 levels. We had level 1 here, we had level 2 here, and our final level, which is level 3. Now level 1 has valid subsets. Level 2 has valid subsets as well. However, the problem is they don't have all the subsets. But then from my example here, we can see that we only get to all of the valid subsets on the last level. So it's important to know how do we determine that we are at the last level so that we will append all the subsets that we have from that level. So that's something that we are going to be implementing as well. Let's just dive into the code, and I'm going to write the code out so that I can go back between explaining why I'm writing some of the code and the influence from the decision tree illustration. So our function def, we'll call it subsets, and I believe they just give you nums, the array nums. So the first thing is, from the example here, you can see that the return type is always going to be a list of lists. So we are going to initialize our return data structure, and we'll just make it a list, an array. And then to implement all that we see down here, we need to implement a depth first search algorithm. And you can fairly like just implement it in the function, but I like to implement those things usually as helper functions because it requires passing less input parameters, and overall I think it makes the code kind of clean, so we'll do that. So our helper function here, we'll call it DFS for the first search, and to take as parameter I. Okay, so now the first thing when you write like the first search or like any of these recursion type of algorithms is to implement some sort of base case. Now our base case is going to be this down here. It is determining when we have got to the leaf nodes. So that's what our base case to be. And the only way we can determine that is to say if I is greater than or equal to the length of nums. Why? Because you realize that we only got to level 3 when we were on our last number in the array. So that is how you are going to determine that. And another thing to pay attention to is that for all these subsets, they are, as you can see, they are their own lists. So we need to add a different type of list that is going to take a snapshot essentially of all the subsets one at a time, and then append it into our res data structure here. So we'll call that subset ARR and make it a global array so that it's easier to access. So whenever we have I greater than or equal to length of nums, we know we are the leaf nodes. And what we are going to do is say, okay, res, we are going to append our snapshotting data structure, and to do that we will say r.copy. And just for implementation, sometimes this operation can be quite costly, so what you can do instead is, instead of r.copy, do r then this string manipulation trick. So you can do either one, but for the context of this, let's just do array.copy. I like using those methods, makes me feel cool, so we'll do that. And then we are going to return. And now we have essentially got to the fun part. That is these decisions we are going to make. So we have two decisions, decision to add and decision not to add. And to add, I mean to add our current number or not to add our current number. So let's do that here. I'll write a small comment here and say decision to add. So what that look like would just be, would just be the array that's taking a snapshot dot append nums at I, and then we will run a depth first search on the number right after it. Why do we do that? Going back to this tree, you see, after we appended, considering our first number, which is 1, when we take 1, we append it, then we run depth first search on that 1 as well, right? And that would include the next number, which in this case is 2. That's on the left side. On the left side here, when we choose to add again, it becomes 1 and 2. And when you go down further to the left, you see that we run the depth first search on the next number after the 2. That's why when we add it, it becomes 1, 2, and 3. So that is why we are running depth first search on the number after it. So that's for the left side. And the right side, what we are doing essentially is not to add the number, but then we have already added the number. So really all we have to do is to pop it. So we'll do array.pop. And then similar to what we had on the left hand side, we also have to write the depth first search on the next number and then on the next number like that. So our depth first search I plus 1 as well. And then we're essentially done with our helper function and really all of the code. So the next thing to do, and how to make sure this is outside of your helper function, is to run depth first search on 0, because that is where we are starting from. And then we are going to return res. Yeah, so as you can see here, this is the code for the subsets. I've written, I wrote out. We have our res, which is going to return the eventual list of all the subsets, and then our base case to identify that we are the leaf node and the decision to add and not to add. So you run it, it's working, and submit it, and yeah, that's pretty good actually. Thank you.